Hello, class. Welcome back to our continuing discussion of u-substitution. So today I wanted to talk about u-substitution questions and what happens when something goes wrong. You pick the wrong u or you make a mistake. So in this video I'm going to show you a bunch of different sorts of mistakes that you could make, how to identify them, and how to fix them. So I'm going to start with the integral of cosine of x over 1 plus sine of x squared dx. Now, there's a few things that could go wrong here. One thing that you might try, for example, is that you might say, well, in the last video, Tommy said if there's a fraction, you might try u to be the denominator. And so you might try u to be 1 plus sine of x all squared, in which case du is 2 times 1 plus the sine of x times the cosine of x. And we're going to have a bit of a hard time making that appear, because remember, ultimately, we're going to have this du, we're going to have to somehow find that in there, because we have to get rid of this dx. So the thing I get from my du is going to have to be part of the integral, or I'm going to have to make it appear in the integral. Okay, so here's just a general hint. If your du is not in the integral at all, something has gone wrong. Okay, so maybe you look at this and you say, aha, well, the thing I see up here is a cosine, so maybe I'm supposed to take u to be equal to sine of x, because if u is sine of x, then du is cosine of x dx. And that's really smart thinking. You're already thinking before you even pick your u what the derivative of that u is going to be, so that it's something that you can pick out. Okay. So if you do this, then this integral becomes the integral of 1 over 1 plus u squared du. So I combined these two into a du, it's a 1 plus u squared, and so then I get here. Now, at first, you might look at this and think, oh, isn't that the arctangent one? But sadly, no, this isn't the arctangent one, because the arctangent one, that would be, that is arctangent. This, I don't know how to do immediately, although you might realize at this point that what you actually can do to finish this is you can do u-substitution again. So I can take v now to be this thing that's in parentheses in the denominator, 1 plus u. So then dv is just the same as du, because the derivative of 1 plus u is just 1. So dv and du are the same. So then this integral here becomes the integral of 1 over v squared dv, which by the power rule is minus 1 over v plus c. And then I have to go ahead and back substitute, so I have to translate everything backwards. So that is the same thing as minus 1 over 1 plus u plus c, which is the same thing as minus 1 over 1 plus sine of x plus c. Okay. So that all worked out okay. Although we had to run through two different u substitutions in order to get the answer, and so I had to translate back, because really now instead of the traditional translating back and forth between two languages, we actually were translating between three languages. The X language the problem was given to us in, but then also the U language we made up, and then the V language we made up. And so that ended up being a little messy. And in fact, it didn't actually have to be that messy, because I could have chosen, so here's an alternate solution. So instead of going for u equals sine of x here at the beginning, I could have realized that actually instead of just sine of x by itself, I could actually take u to be 1 plus sine of x. So then du, and that actually leaves du still as cosine of x dx. So the integral of cosine of x over 1 plus sine of x squared dx, that's the integral we're working on, that becomes just immediately the integral of 1 over u squared du, which is minus 1 over a u plus c by the power rule, because this is u to the minus 2, which is then the same thing as minus 1 over 1 plus sine of x plus c. So there's lots of paths through u substitution questions, and some of those paths will get you to the right place, and some of those paths that do get you to the right place are easier than others. But it's important to be flexible and be willing to try a bunch of different things. So speaking of trying a bunch of different things, I want to do an example where I think it's not super clear from the beginning what the correct u is. So I'm going to take here the integral of tangent cubed of x divided by cosine squared of x dx. And I want to notice there's a lot of different things here that are actually sort of inside functions. I can see at least 4 things I might take. I might take u as the tangent of x. I might take u as the cosine of x. I might take u as the cosine squared of x. Or I might take u is the tangent cubed of x. All of these look plausible from the get-go. So how do I have to decide which one of these is actually going to work? Because only one of these is going to work. Well, I want to calculate what the du's are. dx, du is minus sine of x dx. Du is 2 times cosine of x times minus sine of x dx. That's a chain rule question, by the way. I just skipped to the answer, but if you want to know where this came from, that's the chain rule. And here, du is 3 times the tangent squared of x times the secant squared of x dx. Okay, so what am I looking for in a u? Which of these do I like the best? Well, what I'm looking for in a u, remember from the previous example, is I want du to be somewhere in the integral. And so I look down here and see, okay, well, here's du is secant squared. I don't see a secant squared. Here's du is minus sine x. I don't see that. Here's a du is minus 2 cosine x minus sine x. I don't see that. And then here's a 3 tangent squared secant squared. I don't see that either. Okay, so maybe at first blush, none of these are here. But if I look back at secant squared, I remember what is secant? Secant is the same thing as 1 over cosine. And so the secant squared is the same thing as 1 over cosine squared. Okay. And that I do have, because that is right there. So actually this, of the four, this is the one I want to use. The others you can try, but I do not think any of them will work out for you. And so when you do this, you end up translating this, and so tangent is u, so this is u cubed, and then that all is du. So this is u to the fourth over 4 plus c, and then I can back substitute, and so this is going to be tangent to the fourth of x over 4 plus c, and that is our answer. Again, be willing, if you need to just write out everything and see what works. There's no penalty for trying things and having it not work out. Okay, next up, I want to look at the integral of secant of x tangent of x e to the secant of x dx. Okay, so here, when I go to look for my inside function to be my u, because remember I want my u to be something that's inside another function, the thing that leaps out is this secant of x. So I'll write down u is secant of x. So du is the secant of x times the tangent of x dx. And so as I am working with this, I see, okay, that's a u times the tangent of x times e to the u dx. And so I look at this and I say, okay, but now I need to deal with this dx piece. But how am I going to deal with the dx piece? Because I need a secant of x to do that. Well, you might realize I got a little overzealous here. This u is a secant of x. I just translated it to a u, but I actually want to use this secant. So I want to rewind a second, not do that. I want to actually use this secant as the secant in the secant of x tangent of x. So namely, I want to write this as the integral of e to the secant of x times secant of x tangent of x dx. Okay, and now that, instead of viewing this secant as being by itself a u, I'm viewing this secant, tangent, and dx, those three together, as a du. So this integral is just the integral of e to the u du, which is e to the u plus c, which is then e to the secant of x plus c. Okay, so what's the lesson here? The lesson here is that actually you want to find your du first before you start replacing everything in sight with the u's. Because you absolutely have to find a du. You have no choice because the du is the only way you can get rid of a dx. So that's the lesson. Find the du first. And then after you've found the du, go back and try and translate everything into u's. Because you don't have any idea how many u's you're going to use, but you know you're going to use exactly one du. Okay, I'm going to do one more example here for this video, just to show you a little bit of how flexible u-substitution can be. So I want to do the integral of x to the fifth times the square root of 1 plus x squared dx. Okay, now when I look at this, there's only one function here that's inside another function, and that's 1 plus x squared. So I'm going to let u here be 1 plus x squared, so that du here is 2x dx. Okay, now there are a few things that already might concern you. Namely, when I look at this pair of u and du, especially after the past two examples, I'm expecting to see a du somewhere already in the integral, but I don't have an x. I also don't have a 2, but we know at least how to fix the 2. But here's what I can do. This x to the fifth, that's actually 5 x's. So I'm just going to borrow one of the 5 x's. So I'm going to rewrite this as x to the fourth times the square root of 1 plus x squared times 2x dx with a 1/2 out front. Okay, and so here I did two things. One is I broke up the x to the fifth into two pieces, one x to the fourth and one x, because remember x to the fourth times x is x to the fifth. You add the exponents, the 4 and the 1. And I got the 2, I borrowed this, and I paid for it with the 1/2 out front, because 1/2 times 2 is 1. So this integral here in red is exactly the same as the integral in black. Not for any calculus-y reasons, I just did some algebra to rewrite everything. And I did all of that so that I could make my du appear here. And so when I do that, I get 1/2 the integral of x to the fourth times the square root of u du. Okay, but notice there's a problem here. Namely, what's the problem here? The problem is this integral still has x's in it, and in order for u-substitution to work, there need to be no x's. Which means somehow I need to deal with this x to the fourth. I'm not going to make any progress until I get rid of this x to the fourth. Okay. Now, probably what happens if you're doing this on the homework at this point is that you say, hey, maybe I chose the wrong u because I couldn't get rid of all of the x's. So you go back and you try a different u. Except you're going to realize pretty quickly that there's not any other reasonable choice for u. And so you might try some unreasonable choices for u. Why not? But none of them are going to help. And the reason for that is that this is the right choice for u. We just have to work a little bit harder. Namely, I want to rewrite this x to the fourth as being 2x squareds multiplied together. Remember, again, you add exponents. Okay. And I want to notice that x squared actually is pretty closely related to u. Namely, x squared is u minus 1. And again, where do I see that? I look at this equation that I've underlined in blue, and I subtract 1 from both sides, which on the right-hand side leaves x squared, and on the left-hand side leaves u minus 1. So because u is literally the same thing as 1 plus x squared is literally the same thing as u minus 1. Okay, and so that means I can rewrite this in this fashion. And once I've done this, now I have solved my problem. There's no x's left. And so I can go about solving this integral. Okay, so I'm going to multiply that out. So it's going to be u squared minus 2u plus 1 times. And in order to deal with the square root of u, I'm going to write that as a u to the 1/2. Okay, so continuing dealing with exponents, when I distribute this u squared times u to the 1/2, remember you add exponents, so that's going to be a u to the 5/2 minus 2u to the 3/2 plus u to the 1/2 du. And I can now do that integral. I'll come over here and continue from there. So this is 1/2 times, 1/2 times, and now I'm actually going to do the integral as I promised. U to the 7/2 over 7/2 minus 2 times u to the 5/2 over 5/2 plus u to the 3/2 over 3/2 plus c. Clean that up a little bit. So all of these 2's are going to end up in the numerator, so I can cancel this 1/2 with each of these 2's. And so this is going to equal u to the 7/2 over 7 minus 2 u to the 5/2 over 5. You could put this 2 in the numerator of the fraction or out front, whichever works for you, plus u to the 3/2 over 3 plus c. And so last up, I need to remember this is a u-substitution problem, so the last step in a u-substitution problem is always to put back the thing that we decided was u. So the thing we decided was u in this question was 1 plus x squared. So I'm going to go back and say, okay, so this is 1 plus x squared to the 7/2 over 7 minus 2 times 1 plus x squared to the 5/2 over 5 plus 1 plus x squared to the 3/2 over 3 plus c. And that is our final answer. Okay. I'm going to stop this video here. So this video has the most complicated u-substitution questions where things go wrong and you have to sort of figure out how to fix them. So if you're struggling with u-substitution, you definitely want to come back and look at this video and look at how you can tell when things are going wrong. So far, though, we've only talked about using u-substitution for indefinite integrals. So in the next video, we're going to talk about using u-substitution for definite integrals. And then before the end of the week, we're also going to talk about using this kind of question in combination with questions where you're finding the area between curves in various capacities. But until next time, be well.